In the next two videos, we're going to look at two different ways to represent relations. The first is using matrices. That is this video, and I apologize in advance. This video will likely be pretty long because there's a lot to cover with matrices. The next video will be super short, and that is using digraphs. So the first thing that we want to do is know what it's like to represent a relation using a matrix. And essentially, a matrix that is representing a relation is really just going to be a 0, 1 matrix where we have a value of 1 if the ordered pair is in the relation, a value of 0 if the ordered pair is not in the relation. That's as simple as it gets. So using our example here, we have A is 0, 1, 2, B is 1, 2, 3, 4. So obviously A has 3 elements and B has 4 elements that will come into play. And then they give us our relation, all of the ordered pairs that are in our relation. And I want to give the matrix that represents R. So I'm going to write the matrix that represents the relation. So M sub R is typically how we would write that. And I want to know, first of all, how big should this matrix be? Well, if A is 3 and B is 4, that means I'm going to have a 3 by 4 matrix. So, and again, it's okay, and we're going to do that this time to kind of make it easier on ourselves. We've got 3 this way, and we've got 1, 2, 3, 4 this way. And again, if you want to put those values on there, you can. 1, 2, 3, 4. And essentially what I'm going to do is I'm just going to put a 1 if that point is in the relation and a 0 if it's not. So the first thing I do is look at, and again, just in case I wasn't clear about that, the 0, 1, 2 on the left came from A, the 1, 2, 3, 4 on the top came from B. And then I'm looking at 0, 1, and that value is in our matrix. So 0, 1, that value is in our matrix, so I put a 1. Then I look at 0, 2, and that value is not in our matrix, so I put a 0. Is 0, 3? Yes, it is, right here, so I put a 1. Is 0, 4? No, it's not, so I put a 0. Then I move on to the next row. 1, all of those values. So is 1, 1 in my matrix? Yes, it is. Is 1, 2 in my matrix? Yes, it is. Is 1, 3? No, it's not. But 1, 4 is, and so I put a 1 there. Then I move on to the 2's. 2, 1 is not in my matrix, but 2, 2 is. And then 2, 3 and 2, 4 are not in the relation. So this is the matrix representation of relation R. I wanted to look at just one quick example working backwards as well. I think it's pretty easy to make the matrix. I also want to make sure you understand how to sort of decode the matrix. So again, it's okay for you to cheat a little bit and put the values on the left and on the top, or however you want to do it, but you don't have to. I'm just putting them there for our benefit. So really now I just want to write the ordered pairs that are represented in this relation. And so my first ordered pair would be A1, B3. My second would be A1, B4. And then I also have A1, B5. And then I would move on to the next row, which would be A2, B1. And then I would have A2, B4. And that's all for A2s. And then I would have A3, B1. And I would have A3, B3, which is this guy right here. And I would have A3, B5, which is this guy right here, and that would be the relation. We have already talked about what all of the properties of matrices are, and so I'm not going to spend a ton of time on that, but I do want to show you the advantage of writing your relation as a matrix, because we can visually determine if our relation is reflexive, symmetric, etc. So I'm going to show you how to do that. So recall that if something is reflexive, then A comma A is always in the relation. And in a matrix form, that means that that first diagonal is going to all be ones. And it doesn't matter what other elements are. So it can be zeros otherwise, it can be ones otherwise. It really doesn't matter what else we have. We just need that diagonal to be 1. And I'm sorry that I should have specified. We're talking about a relation of a set onto itself, which is always going to be a square matrix. So if you're like, wait a minute, I don't have a diagonal that works out exactly like your picture, which I know is beautiful, we're only looking at a square matrix because it would have all of the values along here and the same values along here, so obviously it would be square. Another very easy property to determine just by looking at a matrix is the irreflexive property. So if the reflexive property told us that A comma A had to be in the relation, the irreflexive property says A comma A cannot be in the relation. And so again, we're looking at A comma A not being in the relation, so the entire first diagonal should be all zeros instead of all ones. So for our relation to be symmetric in a matrix, what we're looking at is if AB is in the relation, it implies that BA is in the relation. So there's two ways that you can look at this. You can either look at it as folding our matrix along our first diagonal, and if we fold it along the first diagonal, it essentially should match up on each side of that diagonal. The other way to think of this is if our matrix is equal to the transpose of the matrix. And remember, the transpose said if I take all of my columns and turn them into rows, would it be the same matrix? So that is another way to check. The easiest way for me is to just, like I said, fold it along that first diagonal, and if everything matches up, ones match with ones, zeros with zeros, etc., then we're okay. To be antisymmetric, we're saying that if AB is an R and BA is an R, then it is implied that A is equal to B. And so in order for us to show that in a matrix, or to be able to visually see that in a matrix, it means that either Mij has to be 0, which means that either Mij needs to not be in the matrix, or that Mji is equal to 0, or that that value is not in the matrix, or both. But they can't both be ones, otherwise it's not antisymmetric. So notice here I've got a 1 that if I fold it in half matches with a 0 if I fold it in half matches with a 1, or a 0 if folded in half matches with a 0, then it is antisymmetric. But if I had a 1 here and a 1 here, now all of a sudden it's not antisymmetric anymore. Now let's look at a couple of operations on matrices, and again, these should just come right back to you because we've reviewed them this year, talking about how to find the union of matrices. In this case, the union of matrices would really just be the OR. So remember we talked about meets and joins. So this is the MG or MS, which means if either one of the values is a 1, then I get a 1. So I'm comparing 1 to 1, and I get a 1. I'm comparing 0 to 0. Neither one are 1s, so I get a 0. And then I'm comparing 1 and 1, and at least one is a 1, so I get a 1. For the next row, 1 with 0 gives me 1, 1 with 1 gives me 1, and 0 with 0 gives me a 0. So the only time I put a 0 down is if there's no 1s at all. 0, 0 gives me 0, 1, 0 gives me 1, and 1, 0 gives me 1. So that is the first one. For the second, the intersection, really what I'm doing here is looking at MG and MS, which means they both have to be a 1 for me to be able to use it. So again, I'm comparing 1 to 1, and that's a 1. And 0 to 0, obviously is 0. 1 to 1, and that's a 1. Remember, they both have to be 1s. 1, 0 gives me a 0. 1, 1 gives me a 1. 0, it doesn't matter, gives me a 0. 0, it doesn't matter, gives me a 0. 1 with 0 gives me 0, and 1 with 0 gives me 0. So there are the union and intersection of my matrices. So let's look at two more operations on matrices, or two more operations on relations that are represented by matrices. And the first is composition. And in composition, essentially what we're going to do in order to find the composition is to take the Boolean product of the opposite order, because with composition we always really go in the opposite order. You start from the inside out, etc. So this is actually the matrix that represents the relation S with the Boolean product of the matrix that represents the relation G. And so what we're doing here is this one, remember, gets a little bit complicated. This is where I'm going to take the first row of MS, and I'm going to think about it as a column. It's 1, 0, 1, so I'm just rewriting that first row. And remember, I'm going to look at 1 and 1. And so instead of having to write 1 and 1, I'm just going to write that 1 and 1 would be 1. And then remember, it's an OR, and then 0 and 1 would be 0, and 1 and 0 would be 0. And remember, those are ORs, and so what I'm going to be looking for is at least one to give me a 1 over here. And then I'm going to do the next row, the next column. So 1 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1. So that means this is a 1. And then 1 and 1 is 1. And I really don't have to check the rest, but that would be 0 and 1. And so I've got 1, 1, 1 as my first row. Let me write those a little better. 1, 1, 1. And then I would just do the same thing, and I'll switch up colors so we can see. Now I'm going to use 0, 1, 0. And I'm going to do the same thing. I'm going to take 0 and 1, which is 0, 1 and 1, which is 1, and 0 and 0, which is 0, and then 0 and 0, which is 0, 1 and 1, which is 1, 0 and 1, which is 0, and then 0 and 1, which is 0, 1 and 0, which is 0, 0 and 1, which is 0. So my next row is 1, 1, 0. And then last time through, let's use yellow. And I'm taking 0, 0, 0. And we can pretty quickly see that we're just going to end up with zeros here because we can never possibly have two 1s. So that would be 0, 0, 0. So that is the composition, which is essentially just the Boolean product in the opposite order in which the matrices are given to you. Now, if I take matrix S and square it, it's really kind of the same thing that we just did, except I'm doing it with matrix S twice. And so again, I'm going to take 1, 0, 1, and I'm just going to be basically multiplying matrix S by itself. So I'm doing the exact same thing. So that would give me 1 or 0 or 0, 0 or 0 or 0, 1 or 0 or 0, which for my first row gives me 1, 0, 1. And then I will try another color and another row. So 0, 1, 0. So now I would get 0, 0, 0. And I'm not drawing the little loopies this time. 0, 1, 0. And then 0, 0, 0. And that gives me 0, 1, 0 for my next row. And then let's switch colors again. And I'm using 0, 0, 0, which we already discovered last time was just going to be a bunch of zeros because there's no way for me to get a 1 if I'm taking everything times 0. So that is my square. My matrix squared is really just the Boolean product of itself. So now that we know how to do the Boolean product, or we know how to square matrices, what we want to do is look at how to determine if a matrix is transitive. So obviously this one is a little bit more work than the others. The others I can pretty much just look at the matrix and determine whether or not it is reflexive or antisymmetric, etc., etc. So here I actually have to do some work. I have to square the matrix, and what I'm looking for is if I have a 1 in my product matrix, then I need to have had a 1 in the original matrix. So because all of the ones in the product matrix match up with ones from the original matrix, this is transitive. And if I would have had a 1, say here, that it didn't occur here, then it would not be transitive. So in this case, you would have to do the product. So now that we've had a chance to look at all of the properties and we know how to multiply, let's do a practice question like you will have in your homework. So we have a relation represented in the matrix below. We're asking, is it reflexive? Is it irreflexive? Is it symmetric? Is it antisymmetric? Is it transitive? So let's look at all of these together. First one is reflexive. Remember, for it to be reflexive, that first diagonal should all be 1s. That is not the case, so it is a no. Irreflexive means that first diagonal should all be 0s. Is that the case? No, it's not, because we have 1s and 0s. So it's neither reflexive nor irreflexive. For symmetric, remember I'm kind of drawing a dotted line through here and saying if I folded the matrix across that line, do I have the same thing on each side? And yes, in fact I do. So this is symmetric. And if it's symmetric, then no, it is not antisymmetric. Remember, antisymmetric would be if I had a 1 in one of these positions but a 0 in the other, which is not what I have. And then for transitive, I have to do a little bit of work. I have to do the product. So I'm going to take this matrix multiplied by itself, and then see what I come up with. So again, I'm looking at, 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. I'm going to take this first row and turn it into a column and say that's definitely a 1, 1, 1. So 1 or 1 or 1. And then 1 or 0 or 1. And then 1 or 1 or 1. And in my product matrix, I would get 1, 1, and 1. And then I'm going to do the same thing with 1, 0, 1. And I would get 1 or 0 or 1. And I would get 1 or 0 or 1. And I would get 1 or 0 or 1, which is a lot of 1s. And then for my last one, I would have 1, 1, 1, and that's going to give me 1 or 1 or 1, 1 or 0 or 1, and 1 or 1 or 1. And notice I've got a bunch of 1s. Now remember, the test here is if I have a 1 in the product matrix, then I have to have had a 1 in the original matrix. And so if I look right here, I have a 1 in row 2, column 2, but in the original matrix I have a 0. and so this is not transitive. So they would have to be essentially the same matrix when I multiplied them to be transitive.